Today, let's go over another easy question in the 3 series category of depth first search tree traversals. This is the final one called Inorder Traversal. We did pre-order and post-order, and then this is in-order. So simply, if you recall from the last video, pre-order is root, left subtree, right subtree. In-order or post-order is left subtree, right subtree, root. So drawing a picture is probably easier. So root is visited, and then left subtree is visited, and then right subtree is visited. This is going to be for post order. It's going to be left is visited, and then right is visited, and then root is visited. So like this for pre-order, like this for post order, and then in order, lastly, is left, roots, and then right. Everything else stays the same. So left, root, right, in order, right? So our current root is inside, in between left and right. It makes it easier to remember if you think about it like that. So now that we know that, we can use the same recursive strategy to know where to place our append, right? So let's define a recursive function taking in the root, and let's kick off this recursion right here. We're expecting a list of integers, so define an empty list to hold the values. We don't want to hold the tree values, just want to hold integers. And then now define our base case. So before this, let's go over how it's going to look. So we're going to dig all the way down left again. And then instead of visiting 5, or instead of visiting 6, we're going to visit 2 first. And then we're going to visit 6. And then we're going to visit 5. And then we're going to visit 7. And then we're going to visit 9. And then, or we're going to visit 1. And then we're going to visit 3. So inside, in order, this is the current root. And then 9, 8, right? Because 9 is the left and then 8 is the current root. So 4, 2, 6, 5, 7, 1, 3, 9, 8. Again, this part is kind of confusing. So instead of 4, 6, 5, it's 4, 2, 6, 5, not 4, 2, 5, 4, 2, 6, because we still have to dig down left as much as possible first until we hit a none, and then a none, and then we come back, and then now we go back to the root. So the first time we see the root, we're not actually appending anything. That's very important. So let's define our base case. If not root, return none. Again, if we get the 6, we're on the left none child, and then we're on the right none child. Root.left, calling the left subtree, calling the right subtree. And now, because after we finish the left subtree, so for example, all the recursive calls go left, 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 then we're going to return none. So for left is none. And then before we look at the right none child, we're actually going to visit 4, and now we can append it. That's when this comes in handy, because recursive call finishes, 4 is left none child, and then now we visit 4. This is the second time we visited the current node, right? So now we can print root.value. If root is not none, there's always a possibility that it is none, and you'll see the ordering is correct. 1, 3, 2, 4, 2, 6, 5, 7, 1, 3, 9, 8. And now we just append the value to results and then return the result after we finish all the recursive calls. Because again, we're expecting a list of integers. And there you go. Passes all test cases. I think if you remember this and you understand how the code works in the recursion, then it's pretty manageable. So again, thank you for watching, and stay tuned for more.